This is one of those science videos that's going to be 90% math, but we'll do our best to explain what's going on along the way. It's about an infinite time machine called Tipler Cylinder. This was proposed back in 1974 by American mathematician Frank Tipler, who considered the possibility of a massive, infinitely long rotating cylinder that could be used to travel backwards in time. It isn't impossible from a physics perspective. That is, it doesn't violate any known laws of physics. However, the amount of resources required makes it completely impractical. But hey, that hasn't stopped science fiction from running with this idea. After all, there are time machines in plenty of sci-fi universes despite them being impossible, at least for now. So let's talk about how this infinite time machine would work, assuming it's possible in the first place. Now let us say we have this infinitely long cylinder which rotates at some angular velocity omega and has a radius, or the cylinder itself is made of some sort of exotic matter that has negative mass and negative energy density, so that the overall cylinder has a finite total mass and positive energy, even though every little bit of it has negative energy density. As you can see, we've chosen our coordinate system such that the cylinder lies along the z-axis. If you wanted to get onto this cylinder, you would obviously need to climb up it, not sideways. You might ask, why don't we just go sideways? How hard can it be? And the answer is very hard. If you try to go sideways on this thing, it will literally rip you apart. It's because the rotation of the cylinder creates a very strong centrifugal force. In fact, if you were to go close enough to the edge, this centrifugal force would easily overcome gravity and pull you away from the cylinder. The further you get from the axis of rotation, the stronger this effect gets. If you were to get too far out, it would pull you away faster than light, and that would be pretty bad. So yeah, climbing up the cylinder is probably your safest bet, but only if you move in a very particular way. What you can't do is move straight up or down. That's also problematic for the same centrifugal force reasons. You would need to move in a spiral around the cylinder. Now that's not too surprising. We guess that intuitively, but it's actually much more complicated than that. Your spiral would have to be very specific in order for the trip to make sense. And that's because space inside the cylinder needs to be flat. If space wasn't flat inside the cylinder, then parallel transport around the cylinder wouldn't keep things pointing in the same direction. So your trip would end up being very different from what you started out with. Flat space requires that your spiral matches the curvature of the cylinder. In other words, it needs to match the cylinder's circumference at each height. There's actually a formula for this, and it's pretty simple. The distance you need to move in your spiral for every unit of height you climb is given by this quantity here, which is basically the circumference of a circle with radius r divided by the square root of r squared plus y squared, where y is the height you've climbed. Okay, that was the easy part. What happens next is really interesting. Once you're up high enough and you've spiraled all the way around, you simply continue going upwards. Well, not exactly. You see, when you reach the top of the cylinder, if you want to keep going, you have two choices. Either you can continue spiraling around the cylinder and then start going down again, or you can go straight up. Both options lead to the same destination, but going straight up is a lot simpler. And that's because if you choose to spiral around, you'll need to keep matching the circumference of the cylinder at each height, which becomes increasingly difficult the higher you go. As the height goes to infinity, the matching of the circumferences gets more and more problematic. But regardless of whether you go straight up or spiral around, the result is the same. You come out on the other side of the cylinder at a time in the past. Let us say you started at t equals 0 and you went up the cylinder and then out the top. By the time you reach the top, the entire cylinder has rotated a certain number of times, let's say n. Then, after you leave the cylinder, you will reemerge some proper time interval later, and that interval is given by on times to pi over the angular velocity omega, which is the period of rotation of the cylinder. Remember that proper time is the time experienced by an observer, whereas the time in the rest of the universe outside the cylinder keeps ticking away normally. The reason for this is that the cylinder is moving at nearly the speed of light. When you move at nearly the speed of light, time slows down relative to an observer at rest. That's the basic idea behind time dilation. So the time difference between when you left the cylinder and when you come back out is longer than the time elapsed on the cylinder itself. But how much longer? Well, that depends on how fast the cylinder is spinning. The faster it's spinning, the closer the time difference gets to infinity, and the further back in time you travel. That said, the total length of the trip is infinite because it takes an infinite amount of time to climb an infinite cylinder. So in the end, you come out to a time in the past, but you have to take an infinite amount of time to get there. Still, you can kind of interpret this as traveling backwards in time by an amount proportional to the speed of rotation of the cylinder. We know what you're thinking. This sounds cool, but can we actually build one of these things? And the answer is no. In fact, the answer is no, definitely not. For starters, the requirement of negative mass is already a huge roadblock since we don't know if negative mass even exists. If it does exist, then it must be extremely rare because we haven't found any evidence of it yet. Another problem is that the cylinder would need to spin faster than the speed of light, which is a big problem. There's no known physics that allows for anything to spin faster than the speed of light. Not to mention the amount of energy required to get something up to that sort of speed is astronomical. Finally, all of this is based on solutions to Einstein's theory of general relativity, which hasn't been proven to be correct. It might break down at some point in the future, at which point the whole thing would be moot anyway. The issue is that while general relativity works very well and is supported by lots of evidence, it's still a theory. Still, it's always fun to think about these sorts of things. Who knows? Maybe one day we'll figure out how to build one of these infinite cylinders, provided the mathematics is correct. In that case, please send us a message from the past letting us know how wrong we are. Until then, you can watch this video to learn about another mathematical curiosity, the Kelvin monoid, which is basically an infinite sphere.